I was asked by Critical Think channel to respond to Ruif's video titled The Nitty Gritty of Refraction. In Ruif's video, he uses the ideal gas law to come to the conclusion that humidity has a negligible effect on refraction. The problem with using this formula is that it only works hypothetically under ideal circumstances, including standard temperature and pressure. Standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere or at sea level. The problem is gases will deviate from the ideal gas laws when you move away from these standard temperature and pressure conditions.
So, what exactly is the problem with this ideal gas law? Well, if the two sides of the ideal gas law were equal all the time and for all gases, as we would expect for something called a law, then PV divided by nRT should equal 1, as any fraction in which the numerator and denominator are equal. This relationship can be shown graphically, but when you work with real gases in a real lab, it becomes apparent that the relationship isn't constant at all, much less equal to 1. Instead, it changes with increasing pressure, and the amount that it changes is different for different gases. So much for the whole constant thing. So much for the whole constant thing. So much for the whole constant thing.
Gases with large molecules need more correction than gases with smaller molecules. Are the molecules of dry air and moist air the same? Of course not. In fact, dry air has a molecular weight of 60 and water vapor only 18. Instead, we should be using a real-world calculator that takes every real-world variable into account. If we want to find out the effect of a moist air gradient, there is an online calculator already set up to work it out. So what I'm going to do is simple. Work out the percentage change in air density due to the moist air gradient, and then compare the percentage change of air density due to the atmospheric pressure gradient. I'll use the same elevations of 0 and 15 meters as Ruif has used, and the same temperature of 15 degrees C. I'll use a maximum relative humidity of 100% near the water surface and use 30% for the dry air relative humidity. For the atmospheric pressure effect on air density, I simply used the dry air for the air type. So here are the results. The moist air gradient will result in a 0.4% change in the air density from 0 meters to 15 meters elevation. The atmospheric pressure will result in a 0.18 change in air density from 0 to 15 meters elevation. So the clear winner is the moist air gradient, but by how much? Well, the percentage difference is the moist air gradient will have a 222% greater impact on air density than the pressure gradient. Why are my results so different to Ruif's? Because I'm using real-world variables and he's using the ideal gas laws. This is a simple and easy way to find out the effects of moist air on the air density. Why is this important? Light refracts towards the denser medium. Above the water surface, thanks to evaporation, there is a moist air gradient, going from moist to dry air as you elevate above the water surface. If you look at evaporation rate calculators, the wind speed is a big factor. So on days where the wind is up, you may witness even greater upward refraction of light towards the denser, drier air. And what about Ruif and the trolls who refer to his video? I would simply say you need to understand the difference between an ideal gas and a real gas. Thanks for watching. Don't forget to like and subscribe.